Good morning, everybody. Hope you're all healthy and safe. So, let us continue with our section 2.1. We are discussing about solution curves without a solution. So, in today's lecture, what we are going to deal is we are going to discuss more detailedly about what is meant by solution curves and how we are going to interrupt this solution curves for autonomous differential equation. So we have discussed about what is meant by autonomous differential equation in our previous lecture. It basically does not contain the independent variable as in the function on the right side of the equation. So corresponding to this type of differential equation, how will the solution curve behave, or how we can interrupt various things from the solution curves? That is what we are going to discuss in today's lecture. So let's just go through your textbook. So solution curve, this is as it states that without solving an autonomous differential equation, we can say a lot about its corresponding solution curve. So since we are dealing with autonomous differential equations, we can consider the variation of x according to our own will. Either x can vary from minus infinity to infinity, or only the positive axis 0 to infinity, and so on. So the other thing that we have to keep in mind is that since the function f and its derivatives are continuous on some interval, so by our theorem that we have stated, if they are continuous, there will exist a unique solution, right? So we can always find a region where we can find a corresponding point through which the solution passes only once, or only one solution curve passes through that particular point. So you can see in this, that is since we are considering about the function which are derivative or differentiable, so they are continuous also, so we can easily apply theorem. The theorem was theorem 1.2.1. so it stated that if it is continuous, then there exists a unique solution, right? So we can find a point x dot y dot through which the solution curve passes. Only one solution curve passes through this particular point. Okay, so now here what we are going to do is we are going to bring the concept of phase portrait here, which we have seen earlier. And before that, what we'll do is we will divide this whole region R corresponding to the critical points. Now we know what are critical points, right? The values for which y of x equal to c1, those will be the corresponding values for which the function value becomes 0. So this and we'll consider the equilibrium solution, that is y of x is equal to the critical point. That was the equilibrium solution. So this is all these are all things that we have learned in the previous lecture. So here what we are going to do is we are just going to suppose that we have two critical points, c1 and c2, and we are considering two equilibrium solutions, that is y of x is equal to c2 and y of x is equal to c1. c1 is less than c2. Okay, so what we are doing is when we are considering these equilibrium solution, y of x equal to c1 means it is a constant, that is it is a straight horizontal line. So we will divide this particular region R into three regions, right? R1, R2 and R3. Now what we are going to do is, without finding the solution of the differential equation, we are going to say a few things, or we are going to interrupt a few things about this particular solution. Okay, so first the thing is that this solution curve, okay, it will never cross these two lines, y equal to y of x, y equal to c1 and y equal to c2. Why? Because we are considering non-constant solutions, right? And if it has to cross this particular line, that is y is equal to c2, then that solution must be satisfied, that is y equal to c2 must be a solution. But when we are discussing about solution, we are we are not discussing about equilibrium solutions, but rather non-constant solutions. So the solution curve will always lie between these two boundaries. So we know the region where that particular solution will be lying. Okay, now the second thing that which we can get is, in this particular region, in any one of this region, any region whichever we take, the function value must be either, function is what, dy by dx is equal to f of y, that is the function that I am talking about. So that function is either increasing or it is decreasing. Okay, it cannot be both, like it is increasing and decreasing. That is not possible. It will be either increasing or it will be either decreasing. Okay, and also it cannot change the sign also. That is, f of y is either greater than 0 or it is less than 0 in any region if you consider. So if I am considering R1, so here in this R1 it will be either greater than 0 or less than 0. In R2 it will be either greater than 0 or less than 0. In R3 again it will be either greater than 0 or less than 0. So these are a few properties that we can understand from this. Also it is strictly monotonic. Monotonic means just now that I have stated that it is either strictly increasing or strictly decreasing. It cannot be both. And similarly, if y of x is bounded above by a critical point, okay, C1, then what happens is the solution, the graph of y of x will approach the graph of the equilibrium solution either as x tends to infinity or minus infinity. So if you are considering a point here, and if I am talking about the solution curve in this region, then this solution curve will approach this equilibrium solution. It will definitely approach it, okay, either by x tends to infinity or minus infinity. That is depending upon the function being increasing or decreasing, or where the solution curve is lying. Okay, so in any case it will approach the equilibrium solution. So these are the things that we have to keep in mind, and with this we can view a few example related to this concept of solution curves without actually determining what is a solution. So the first thing was that we can always, the solution curve will never cross the equilibrium solution lines because we are considering about non-constant solution. The second thing, in that any region the function will be either increasing or decreasing. It will not be oscillatory. Second, that was it. Then the third one is that the function value f of y will either be greater than 0 or it will be less than 0. And finally, the solution curves in any region will either, it will approach the equilibrium solution. So that can be, the approach can be as x tends to infinity or x tends to minus infinity. That depends upon the function. So these are the things that we can interrupt easily from the solution, from the differential equation that is given to us, and the autonomous differential equation given to us, and the corresponding critical points. So let's just view the example. This was the example which we had done earlier, in which we had got that p is equal to 0 and p is equal to a by b are the corresponding critical points. So here we have two critical points. So this is similar to the concept that we have just now stated. So you can see figure 2.1.6, it is the phase portrait and the solution. The phase portrait is given here. This is a phase line that is from minus infinity to 0. We had said that the function p, that will be decreasing, and from 0 to a by b it is increasing, and from a by b to infinity it is again decreasing. That is obtained if we put the corresponding values, and we can verify that. We have done that in the last section. So now let us, if we are discussing about the solution, so let us we'll again divide the given region into 3. Okay, that is there will be a critical point at a by b, and the critical point is 0. Okay, now let us see if we are considering p of 0 to be p dot, that is the initial value. Now if p dot is less than 0, okay, if p dot is less than 0, then p of t is bounded above, and as the function p is decreasing in the region, first region, it is decreasing. So what happens is it will tend to 0 as t tends to minus infinity, because the function is decreasing. So as t tends to minus infinity, the function will keep on decreasing, or the value of the p function will decrease and it will tend to 0. Okay, so the graph will be as follows. It will be like this. As t decreases, the graph will be approaching to the equilibrium solution, that is p is equal to 0. Okay, Now similar case, if you consider the other region R3, here also that is the region P dot is greater than A by B. In this region, here you can see that the function P is bounded below by A by B, and here again it is decreasing. Okay, so we can say that as t tends to infinity, we can say P approaches A by B. Okay, as t moves, the function is decreasing, so the function is moving downwards. So when t goes to infinity, the function will approach A by B. In this case, what was it? The function was again decreasing, it is approaching like this. So when t goes, when will this curve meet the equilibrium solution? So that is possible only when t is approaching minus infinity. So when t approaches minus infinity, the decreasing curve will approach 0 at some point. I hope this is clear. So this is our t. T acts as actually the x-axis, and our p is on the y-axis. Here we are considering the plane TP plane, not xy plane. We are considering TP plane. So t is the x-axis. So t approaches to infinity, function is decreasing. So in region R3 we will get a figure like this, and in region R1 we will get a figure like this. So that is about the last one, because it is both these regions are bounded by this equilibrium solution. So since they are bounded, they will definitely approach the equilibrium solution. Okay, that was one of the observation that we had made. Now let us come to the second region, R2. So here R2, in R2 P dot is lying between 0 and A by B, and it is bounded by these two lines, right? Now here the function is given to be increasing. So as P is increasing, I can say that it approaches A by B as t tends to infinity. As t is moving like this to infinity, P is approaching A by B, and as t is moving to minus infinity, P dot is approaching 0. Okay, so I hope it is clear. So this is something that we can depict about the about the solution curve. So here in all the three regions, what you can see is that the point P dot is the solution curve passes exactly once along this point P dot. Okay, so that is, it will have a unique solution. This is by the theorem that we have stated in the first section. Okay, so we are we have discussed about the 4 observations that we could make about the solution curves, and we have also seen how we can apply it in this particular region. Now let us move on to the another example about this is another autonomous equation that we are considering. Okay, so this is the autonomous equation. The equation is dy by dx is equal to y minus 1 whole square. Okay, so dy by dx is y minus 1 whole square. So what will be the critical point? Y is equal to 1 will be the critical point, right? Because it is at the point 1, the function value will become dy by dx is 0. So 1 is a critical point. So we just have one critical point. So we can consider the region to be like minus infinity to 1, and the other region 1 to infinity. Okay, so we can consider these two things, and let us consider any particular point like we have done P dot in the previous case. Here I am going to consider y dot. Y of 0 is equal to y dot. Okay, so let's just look into the figure. We have this is our phase line, that is at 1 we separated from minus infinity to 1 and from 1 to infinity. Now corresponding to the function that is the solution, we can see that dy by dx, if you consider the y of x is equal to 1 minus 1 by x plus c will be the solution of this particular differential equation. If you consider differential equation given to us, that is dy by dx is y minus 1 whole square, the solution is y of x is equal to 1 minus 1 by x plus c. Now don't worry about how to find the solution, we will be discussing about it. We will be learning how to find the solutions of a differential equation. Now if you are considering the initial condition y of 0 is minus 1, okay, then minus 1 is less than 1, and we can see that this, if you consider, and y of 0 is 2. These are the two initial conditions that we are considering. Then y of x is equal to 1 minus 1 by x plus 1 by 2, and y of x is equal to 1 minus 1 by x minus 1. Okay, so if we consider the corresponding equation, so we are considering, you can see the differential equation is given here. Okay, this dy by dx is equal to y minus 1 whole square with the initial condition y of 0 is minus 1. So you get a solution as such. Y of x is equal to 1 minus 1 by x plus 1 by 2. And if we consider the differential equation, dy by dx is y minus 1 whole square with the initial condition y of 0 is equal to 2. You get the differential equation to be y of x is equal to 1 minus 1 by x minus 1. Okay, now the solution curves are given here, that is y of x. You can see that in figure 2.1.7b, y of x will tend to 1, that is our solution. It will approach 1 as x is moving positively. And here in 2.1.6 1.7c, you can see that y of x, it tends to infinity, that is moving to infinity as x approaches to 1. As we are moving like this, x is approaching to 1, like so x is approaching from here, it is approaching to 1. So as x approaches to 1, y is moving to infinity. Okay, and as x is moving to infinity, y is moving to 1. So this is our corresponding the critical points, where the dotted lines represent the equilibrium solutions. So these will be the solution curve or behavior of the solution near y is equal to 1. So I hope the concept about the solution curves is clear for you people. So just go through the example and just read the 4 properties or 4 observations that we have made, and how to use them with the corresponding or relate them to the examples that is given to us, and you will be able to understand it clearly. There is nothing much complicated in this. So that was about the solution curves of autonomous differential equation. So that's it. Thank you. Stay safe and stay healthy.